Hi everybody. In this video I want to derive the formula for the potential energy of a spring. Along the way I want to illustrate the fact that the change in potential energy associated with some conservative force is equal to the negative of the work done by that conservative force. And to do all this we're going to consider conservation of energy. Alright, so here we go. Let's imagine we have a block of mass little m attached to a spring. Let's assume that the mass of the spring is so small in comparison to the mass of the block that we can ignore it entirely, so a massless spring approximation. Imagine that all of this is on a horizontal frictionless surface. Let's assume the spring is connected to the wall somewhere over there. So it's anchored. And let's imagine that this location right here is the x equals 0 location, the equilibrium location. So with the mass attached to the spring and with the spring neither stretched nor compressed, the mass would be sitting right here. All right, so over here the spring is stretched a little bit, and over here this would be even further stretched. So now let's imagine that someone has pulled this mass from here to here. It doesn't have to be a constant pulling force. In fact, it probably isn't. We're just imagine that someone has pulled this mass from here to here against the action of the spring. All right, so this F sub p is representing the so-called pulling force. All right. Now, I'm not really going to consider forces directly at all until we get into the utilization of work, which we'll get to in a moment. What I want to do is consider energy conservation, and I want to consider energy conservation from two different perspectives. First, a system consisting of the mass, the block of mass m, and the spring, and a system just consisting of the block, the mass m alone. All right, and we'll apply energy conservation with both these perspectives, and that'll get us to this expression that the change in potential energy associated with the conservative force is equal to the negative of the work done by that conservative force. All right, so here we go. So first, let's consider just the mass by itself, not the spring, but just the block of mass m. So if we consider only the mass as the system, then both the pulling force, shown here, and the force exerted by the spring, which I haven't pictured, but the spring is attached to it, pulling the other direction, those are both external forces doing work on the system. So my energy conservation expression, change in energy of the system, will equal energy transferred into or out of the system by means of work, heat, radiation, etc. Well, radiation and heat are not factors here. I'm not worried about shining light on this and changing the situation. I'm not worried about warming it up over here and having things change. Clearly, those are not important in this situation. But the work done by agents outside the system is important. Well, I've got the work done by the pulling force. And if the system is just the mass by itself, I've also got the work done by the spring force. All right? So that gives us the change in energy of the system. Now, what does the energy of the system consist of for just a simple block? Well, the change in energy of the system would just be the change in kinetic energy of this mass m. All right. So now let's go over to this other way of looking at this situation. Let's look at a system consisting of not only the block of mass little m, but also the spring. All right, so we start with the same conservation of energy type of framework. The change in energy of the system is equal to the energy delivered to that system, transferred to that system by means of work, heat, radiation, etc. Again, heat, radiation coming from outside, not going to affect this. What is going to affect it, however, is the work done by agents outside the system on the system. Well, in this case, the only thing external to the system that's doing work on the system is the pulling force. So we've got the change in energy of the system, consisting of the block and the spring together, is equal to the work done by the pulling force. Note, of course, I haven't drawn a free body diagram. We can imagine forces acting on this thing. We've got the pulling force this way, got the spring force this way. Gravitational force that way, normal force this way. Gravitational force and normal force are not doing any work on this system. They are external. They're external forces, but they're not doing any work on this system because the displacement of the mass is moving perpendicular to those forces. Those forces do no work. All right. So the change in energy of the mass spring system is equal to the work done by the pulling force. All right, but the change in energy of the system of the mass spring system is a little more complicated. I've got the change in kinetic energy of the system. Now, since the mass itself the spring itself is approximately massless, it has no kinetic energy and no change in kinetic energy. So change in kinetic energy here is still just the change in kinetic energy of the block. But now I also have the change in spring potential energy. I'll call the spring potential energy capital U sub s. This is capital U. I'll put little capitals on it. I'll put little capitals over here on this U as well, and this one. So I'm using the symbol capital U for potential energy. And those together will equal the work done by the pulling force. All right. So now we've got two expressions. And there are some things that are the same. This WP and this W sub P, those are the same thing. Those are the work done by the pulling force. This is the change in kinetic energy of the block of mass m. And this, technically, starting would have been the change in kinetic energy of the block of mass m and the change in kinetic energy of the massless spring. But the massless spring has no change in kinetic energy. So this delta K is the change in kinetic energy of the block of mass m as well. All right, so let me just rearrange this expression. I'm going to subtract the work done by the spring from both sides. All right, and now these expressions look very similar. I've got change in kinetic energy here. I've got plus the change in spring potential energy equals the work done by the pulling force. Here I've got the change in kinetic energy plus the negative of the work done by the spring equals the work done by the pulling force. All right, if this is equal to this and this is equal to this, then this has to be equal to this. So we get the result when we put these things together, those equations. We get that the change in spring potential energy is equal to the negative of the work done by the spring force. All right, so really I've shown this in a highly specific situation. I've shown that the change in potential energy associated with the spring is equal to the negative of the work done by the spring. It turns out this is a more general relationship, or a similar relationship applies to all conservative forces. The change in potential energy associated with the action of some conservative force is equal to the negative of the work done by that conservative force. All right, so if we want to get an expression for potential energy of a spring, what I ought to do is try to calculate the work done by that spring. And then maybe this expression will drop out. So let's give that a shot. The change in potential energy associated with the spring will equal the negative of the work done by the spring. All right, so let's go back up to our picture here. What I want to do then is calculate the work done by a spring going from some initial x-coordinate to some final x-coordinate. All right, so I better review work very briefly. Work in general has this expression. It's a dot product of a force and a differential displacement and added up under an integral. So in other words, I may have a force that's changing, could be changing magnitude and changing direction, and I could have a displacement that's continually going in different directions. But if I take a dot product of force and an incremental little displacement, I'll get a little bitty bit of work. If I add up all those little bitty bits of work over the whole path from initial location to final location, I'll get the total work done by that force along that path. In principle, this can be very complicated. Often in introductory physics, we end up working with a couple of special cases. First special case is a case of a constant force, that's a force with constant magnitude and constant direction, and a straight line displacement. In that case, you just take the dot product of the force and the displacement vector, and you get the work done by that force. There's another special case that's not this full-blown case, but it's special in a different way. We can imagine a variable force vector, but having a displacement only along the x direction. Well, then the dot product will pick off the x component of that force, and this work formula will become, in that special case, the case of a variable force with possibly variable direction in a straight line, but a straight line displacement along the x-axis. It'll pick off this part of that expression. All right, so this will be applicable to what we have. The spring force, remember what the spring force is. I should rewrite it right here. All right, so let's do that. Let's calculate the work done going from this x initial to x final. So I need my minus sign. Then I need the work. So I'll go from x initial to x final. I need to put in the force. So this is my expression. But the x component of the spring force is minus k, minus the spring constant, times x. And then I've got dx. All right, so I need to evaluate the integral. So first, let me just pack out what change in potential energy is. That's just potential energy final minus potential energy initial. All that will equal this. Now I've got minus and a minus, so those will cancel. I've got integral kx dx. So integral of that's going to be 1/2 kx squared. And I've got to evaluate it at the limits. I'll just put the limits here. I didn't really leave myself enough room. Going from x initial to x final. This is representing at the top of the limit. I just didn't have room for it. All right, so remember how that happens, right? Integral x dx is x squared over 2, or that's the antiderivative. If you have a definite integral, you have to put the limits in. So we evaluate this at the limits, and so I'll have 1/2 kx final squared minus 1/2 kx initial squared. So that is the final potential energy minus the initial potential energy is this minus this. So from that, we infer that the potential energy of the spring, and I probably could have had a S subscript on here as well. I've just left it off here. That spring potential energy has the functional form 1/2 kx squared. OK, so there's the spring potential energy. Thanks for your attention, and I'll see you in class.